Hello my dear children of class 11 science. Today I welcome all of you again through this mode of teaching. The mode that we are following is called YouTube mode, and in today's class we do continue with the chapter flows of liquid. Okay, the flow of what? Liquid. This is one of the chapter, as I said, under unit number 7, and in today's class we study one of the important theorem, and this is called Bernoulli's theorem. Okay, one of the theorem called Bernoulli's theorem. Now in the last class we had done up to the topic called Bernoulli formula for the flow of liquid through a pipe. Okay, and after that you learn the different energy of a flowing liquid. Means when the liquid flows, the liquid possesses basically three type of energies. One is called pressure energy, then after kinetic energy, then after you learn potential energy. Now this kind of energy of the flowing liquid can also be possessed when that liquid flows through a tube, Okay, now the tube we consider as an imaginary tube, and we call this tube as streamlined tube. And children, basically when we state Bernoulli's theorem, this theorem give a statement by taking a liquid, and you have learned already, the children, the liquid we had discussed is called ideal liquid. And you know, ideal liquid are always incompressible liquid and non-viscous liquid. But this theorem is applied not only for liquid, it is also for gases. The gas can be ideal gas also. Okay, so the main objective of this theorem, okay, is to conserve the energy, to show the conservation of what? Energy when there is a flow of liquid or gas. So when there is a flow of liquid or gas, in the flow of liquid and gas also the energy is also conserved, and that is actually the main objective of Bernoulli's theorem. But this Bernoulli's theorem has some applications also. Okay, but before we come to the application and all, so let's try to understand the statement of Bernoulli's theorem. So Bernoulli's theorem states that when an incompressible and non-viscous liquid and gas, and you know liquid and gas are also called fluids, okay, and these liquids and gas are called ideal liquids or gas. And when this type of liquid or gas flows in streamlined motion, what motion? Streamlined motion, from one place to another place, then at every point of its path, path, the total energy per unit volume is constant. So what will remain constant? The total energy per unit volume will remain constant. Now total energy per unit volume means the three type of energy outed. As you know, one of the energy is called pressure energy. You have already learned pressure energy, because when liquid or gas flows, we did last time with liquid, but the gas can also flow. Okay, so three type of energy can possessed by this liquid or gas, which are called fluids. One is called pressure energy, then after you learn about what energy? Kinetic energy, and there is one more energy that is called potential energy. So this pressure energy, kinetic energy and potential energy are also the total energy that remain constant per unit volume when the incompressible and non-viscous liquid and gas flows in a what motion? Streamlined motion. And this is the statement of Bernoulli's theorem. Okay, this is the statement of what theorem? Bernoulli's theorem. Now this statement of Bernoulli's theorem can be written mathematically. Means we write the statement mathematically also. Now it said that total energy per unit volume is constant. The total energy means one is pressure energy per unit volume, and you know pressure energy per unit volume is given by P plus kinetic energy per unit volume, and that is given by half rho B square. This is the kinetic energy per unit volume, plus potential energy per unit volume, and that is also given by rho GH. So pressure energy per unit volume plus kinetic energy per unit volume plus potential energy per unit volume remain constant. That is equals to constant. Constant means it remain conserved. And this is the statement, mathematical statement of Bernoulli's theorem. That's why children, I already said that Bernoulli's theorem main objective is to show the principle of conservation of energy. That means the energy is also conserved when there is a flow of liquid or gas. And these three energy which remain constant when this incompressible and non-viscous liquid or gas flows in streamlined motion. Okay, so this is the explanation of Bernoulli's theorem. Now we come to the proof of this Bernoulli's theorem. Yes, because sometimes you will be asked to prove the Bernoulli's theorem also. So in order to prove the prove the Bernoulli's theorem, we take a streamlined tube. What tube? Streamlined tube having different area cross section. Now children, in order to prove the theorem, as I said already, we take streamlined tube. This is a streamlined tube having non-uniform cross section area. So this is a tube that is called XY, is a non-streamlined tube having this end as area, and this area I consider say A1. So area of end X of the tube is A1. There is another end of the tube that is Y, and this end also has an area, and that area I consider as A2. So what is A1 and A2? These A1 and A2 are the area cross section of the two ends of the tube, which are not same. So let me consider the liquid flows through this tube. But what type of motion the liquid occurs in this tube? Streamlined motion. And you have learned what is streamlined motion. So in this case, what happened? The liquid enters from one end and liquid end leaves from other end. So when liquid enters from at this end, it enters with a velocity, and this velocity is given by v1. When the liquid leaves from this end, it leaves with a velocity. Okay, you can see the diagram, and this velocity is what? v2. So b1 and b2 children are the velocity of liquid entering at an x and leaving at an y. So at the same time, if this is an area in which the liquid entering with a certain force, then there is a pressure exerted by the liquid, and this pressure I consider as P1. And this is the end where the liquid leaves from this end, then with a force, then there is a pressure exerted by the liquid, and that pressure is considered as P2. That is how much? P2. So the liquid which enters at an X must leave from an Y. But look at the diagram children. This tube having different non-uniform area cross section is placed on the surface with a different height, and one of the height is H1, that is the end, the height acquired by the end X of the tube from the ground, and there is a height also acquired by the end Y of the tube, that is S2. So in order to prove the theorem, so I have just considered some part. You can see P1 and P2, these are the pressure at an X and Y, that you can see the diagram also. B1 and B2 are the velocity of flow of liquid and X and Y respectively. Okay, means B1 is the velocity of liquid which is entering at an X, B2 is the velocity of liquid which are leaving from an Y. Now the most important part that we need to start from this proof to prove the theorem is the liquid which definitely enters at an X. So that the liquid which enters at an X travels certain distance, just in how many seconds? 1 second. And that 1 second liquid definitely travel with a velocity. And you know distance means what? Velocity into time, because velocity means distance by time. So the distance which is traveled by the liquid to enters at an X just in 1 second is equals to the velocity of the liquid, because velocity is v1, time is 1 second, means v1 into 1 means what? Distance. So what I do, I write down. So by what distance the liquid travel, means liquid enters just in 1 second through this end X, that is equals to b1, because b1 is the velocity and time is 1. So velocity into 1 means distance travel by that liquid entering and at X in 1 second, so equals to b1. So if liquid travel a distance this much, then there is a pressure which is also exerted by the liquid at an X, and that pressure we have already assumed, and this is the pressure P1 exerting on the area A1. So if there is a pressure exerted on the an X of area A1, then there is definitely a force exerted on the liquid at an X, and this force is given by P1 into A1. See, force, pressure means force by area, so that force equals to pressure into area. Pressure into what? Area. So area is A1, pressure is P1. So P1 into A1 measures the force acting on the liquid at an X. Now children, we can measure the work done, because when there is a force exerted on the liquid and that liquid have a displacement or distance travel in 1 second or so, definitely there is a work done also. And this work done also children we calculate in 1 second. So work done per second on the liquid entering the tube at an X. So liquid which are entering at the tube an X is equals to force exerting on the liquid just in how many seconds? 1 second, and distance traveled by the liquid entering at an X just in 1 second. Okay, so force, we have already calculated as pressure into area, P1 into A1, force into what? Distance traveled by the liquid which is entering at an x in 1 second is what? Equals to B1. So how much work done now is calculated? P1 A1 into B1. Similarly, children, we can calculate the work done per second on the liquid which are leaving from the tube T or from the tube and Y. Okay, but this work done is calculated against the force. Against the what force? Now why against the force? Because if you look at this diagram, children, this is the end where the liquid are leaving, but at this end the pressure is exerting in this direction, and this pressure is exerted by the atmospheric pressure, okay, on the liquid, because of the force exerted on this direction. But still against this force also what happened? The liquid is leaving out, but just in how many second? 1 second. So in that case also we need to do the work, and that work done per second that we are calculating at an x and y can also be calculated similar like the work done per second in which the liquid enter at an x, and it is given by P2 into A2 into B2. So just look at this. This is similar like this one, because P2 into A2 means pressure into area at the end y means what? Force into B2. As you know, B2 is the distance traveled by the liquid just in how many second? 1 second. Okay, when it leave from the end y. So that's why that force into distance means work done. But this is for 1 second only, children. This is only for what? 1 second. So these are the two work done per second on the liquid entering and leaving at an x and y respectively. So under this case what we do? We calculate the net work done. But children, remember this is the positive work done and this is the negative work done. So when we calculate the net work done is always the positive work done minus negative work done, because this work done is against the force and this work done is by the force. So children, as I said already, I will calculate the net work done, and net work done per second on the liquid is equals to P1 A1 B1 minus P2 A2 B2. So this two work done, differential work done, means the net work done. Now after this, what I do now is I am going to apply one of the principle that you have learned already, that is called principle of continuity. Children, you know why principle of continuity we need to apply out here? Because when the liquid are flowing in that tube, whatever motion is occurring by that liquid, streamline motion, the flow is streamline flow, and the tube that we are taking is streamline tube. And you have learned already, children, that when there is a liquid that is called incompressible and non-viscous liquid flows in a streamline motion in a tube, at every point of the tube, okay, every point of the liquid, the product of area cross section and the velocity of flow is also remain constant, and this is actually the principle of continuity, okay, of flow. So children, I apply principle of continuity, and principle of continuity can be simply written as the product of area and velocity at every cross section of the tube remain constant, and we have taken two ends of the tube, one is nx and another is ny. At nx, what is the area cross section? A1. What is the velocity? B1. So product is A1 B1 equals to nx and y, area cross section is A2, velocity is B2. So product is A2 B2. But this area and this velocity means actually the distance traveled in 1 second is also the volume of the liquid. So this product is actually the volume of the liquid which is entering at an x and leaving at an y. Okay, so that means this relation is actually equals to the volume of liquid which is entering and leaving at an x and y. And volume can also be expressed in terms of mass and density. Density means mass by volume, then volume means mass by density. So this product, children, is also equals to mass by density. M is the mass of the liquid entering and leaving at an x and y. Rho is the density of the liquid. Okay, so A1 B1 A2 B2 now I can replace by M by rho. Now this relation now I substitute in this net work done, because in net work done A1 B1 and A2 B2 is also there, so I replace in this. So I write down therefore the net work done. Net what? Work done per second. Net work done what? Per second on the liquid. On the what? Liquid is equals to P1. See, P1 A1 B1, but A1 B1 I write down as M by rho, m by rho. See, A1 B1 means m by rho minus P2. Now A2 B2 is also m by rho, so I write down m by rho. Okay, so you can see what is common in the expression. M by rho is common. So inside the bracket is P1 minus what? P2. So the net work done per second on the liquid which are entering or leaving is also can be expressed by m by rho bracket P1 minus P2. Okay. Now there are other part that we need to do so that I can prove the Bernoulli's theorem. Children, I'll do continue in the next YouTube video, so that that video makes the continuation of this particular video, and it proves the Bernoulli's theorem.